trigonometry. And we start with, we have a bunch of stuff to learn today, but this is actually section 6.3, which is called right triangle trigonometry. Let's begin. So the first thing we're going to look at is something called the Pythagorean theorem, which I think we did this a little bit, Pythagorean theorem, but we're going to take a closer look, and we're also going to look at why this is so important and how we use it in trigonometry. It's like just one of the most important things there is. This is the right triangle. This is what a right triangle looks like. It has a right angle, which we indicate by a box. That means a 90-degree angle. And we label the triangle. These are called vertices, the vertex. And when, all of them together are the vertices of the triangle in terms of capital letters. And the Pythagorean theorem basically tells us that this side is called a leg, this side is called a leg, and this side is called the hypotenuse. You always know the hypotenuse because it's the line opposite the right angle. The Pythagorean theorem states that the leg squared plus the other leg squared is equal to the hypotenuse squared. Now, the angles of a right triangle or any triangle are indicated by capital letters. The sides are sometimes indicated by small letters, lowercase letters, and the side opposite the capital A angle here can be written as little a. The side opposite the angle B as little b, and the side opposite and the hypotenuse is known as C. This is where the a squared plus b squared equals c squared comes from, by using those letters as the sides. It doesn't matter, but this is the way it's used. This is the way we're going to be using it this next couple of weeks. So you're going to be given a right triangle. It may not even be lettered, the letters indicated, but you'll be given a triangle which looks like this. And you will be told to find x. And the way you find x in a right triangle is to use the Pythagorean theorem. In other words, leg squared, x squared, plus leg squared, 6 squared, equals the hypotenuse squared, or 10 squared. Leg squared plus leg squared equals hypotenuse squared. Leg squared, x squared, plus 36 equals 100. You do this. Time passes. I used to have a professor in college, and when he did a long proof, he would say time passes, and he would just keep writing and writing. You take the square root of both sides of the equation, and x is equal to 8. Now, I know that some of you might be saying, is that plus or minus 8? Well, not really, because it can't be negative, because we're talking about the length of a line. When you're talking about the length of a line, then you only talk about the positive values. So the square root of 64 would be equal to 8. This is a Pythagorean theorem. And sometimes it doesn't work out so perfectly, It's not going to always work out to a whole number. Sometimes you're going to get a problem where this is x, this is 5, and let's say this is 9, and you'll be asked to find x, and you do this, of course. This is the next step. And x squared plus 25 equals 81. Square root of 56 is the answer. Now, you can't do anything here. This is it. Now, some of you might be saying, hey, why don't you take your calculator and find the square root of 56? Well, you could. I mean, if you were building a house or something and you needed to know how long a ladder was leaning against a building or something like that, then you'd need an approximate value of the square root of 56. But you'll notice that I used a very important word, and the word is the approximate value. So when you use your calculator to find the square root of 56, and it's going to be second function, so the square root will be second function x squared. And you put in the 56, close the parentheses. It's going to be it comes out to 7.48331 and on and on and on. But this is the exact value. When you see a problem which says find the exact value, then you leave it just the way it is. If it doesn't say that, then you can, look at your calculator and put, 7.5 to the nearest 10th or 7.48 to the nearest 100th. But exact value, this is the exact value. The 7.5 is not the exact value. It's an approximate value. Okay, that's the Pythagorean theorem. Are there any questions? Okay, number 2, the 6 trigonometric functions. What do we mean by this? So let's go back to the right triangle. Put the little box there, which means right triangle. This is theta. This angle is theta. You could do that. Rather than call it A, B, C, you could just say, well, the angle is theta. And theta is just, how much the value of the angle is, which we're not interested in right now. But we are interested to know the side over here, which is called the side opposite the angle. So, and I'm going to abbreviate that by OPP, side opposite. This is the side right. I beg your pardon? Okay. This side is called the side adjacent. And of course, the hypotenuse is the hypotenuse. This will be abbreviated simply OPP. This will be abbreviated ADJ, and this will be abbreviated HYP. Now, there's a relationship among the various sides of the triangle. These are called trigonometric functions. For example, the side opposite divided by the hypotenuse is known as the sine of the angle. So the ratio of the side opposite over the hypotenuse is given the name sine. The ratio of the side adjacent to the angle is given the name cosine. Those of you with any kind of experience in this area know all this already, or at least that there's something called a sine or a cosine, and indeed a tangent, which is equal to the opposite over the adjacent. Well, you might be saying, okay, that's nice, Greenhall, but you sort of called this the 6 trigonometric functions. Where are the other 3? Well, I mean, if you can consider opposite over hypotenuse, then certainly you must be saying to yourself, what is the hypotenuse over the opposite? In other words, the reciprocal of sine. And that is equal to something called cosecant. Let me write that so you'll know what I'm talking about. Cosecant. secant. That's what it's called. This abbreviation is for that. But we're not gonna write it out. We're just gonna use abbreviations. As a matter of fact, sine is not really S-I-N-E. From now on, it's S-I-N. Cosine is not the way I spell it here. From now on, it's C-O-S, and tangent is T-A-N. Okay, so from now on, we refer to it as S-I-N, C-O-S, T-A-N. But don't say S-I-N, just call it sine, cosine, tangent. The cosecant is the reciprocal of sine. Secant of theta. I left out the theta, but it doesn't matter. The secant is the reciprocal of cosine. This is called the secant. We won't go into why they're called the secant and all that stuff. Let's just focus on that for the current moment. And the reciprocal of tangent is called cotangent, which can be abbreviated COT, and that will be adjacent over opposite. These are the 6 trigonometric functions. These are the main 3 functions: sine, cosine, tangent. These over here are called reciprocal functions. Reciprocal functions. So these are things you need to know. You need to know what the 3 main functions are, and how, what they are according to the triangle, and you need to know what the reciprocal functions are for each of them: sine and cosecant, cosine and secant, tangent and cotangent. That's what you need to know as of what I just did. Now, how is all this used? So now let's take a look at applications. Okay. So here's a triangle, and let's label the sides as, 3, 4, and 5. Now, if I asked you to find the sine of theta, you would say, okay, here's theta. It's the side opposite. Sine is opposite over hypotenuse. Hypotenuse opposite over hypotenuse. So if you wanted to find out what this sine of theta is equal to, you'd go opposite, which is 3 over 5. So the sine of theta is equal to 3 over 5. The side opposite the angle divided by the hypotenuse. If I said, okay, what's the cosecant? You know that the cosecant is the reciprocal function of sine. See, this is the way, this is your thought process. Your thought process should be the cosecant is the reciprocal function to sine, and therefore it's going to be 5 over 3. Aha. Very helpful to know that. You don't have to know that cosecant is the hypotenuse over the opposite. You have to know that it's the reciprocal of sine. For example, if I asked you for the cosine of theta, you would say, okay, well, it's going to be cosine is adjacent over hypotenuse. Adjacent over hypotenuse, 4 over 5. and cosine of theta is 4/5. If I then said, okay, what's the secant of theta? Well, the secant is again the reciprocal of cosine, and therefore 5/4. And finally, I could say to you, well, let's look at tangent of theta. Tangent of theta is going to be opposite over adjacent, opposite over adjacent, and therefore 3/4, 3/4. Tangent of theta is 3/4. And if I then said, as you might predict, what's the cotangent of theta? You would say, well, that's the reciprocal function of tangent. These, all three of these are the reciprocal functions of these, the big three. This is the big three: sine, cosine, and tangent. These guys have a very special place because they are the reciprocal functions. Cotangent would be 4/3. And that's an example of how you would, given a triangle, given the size of a triangle, if somebody said to you, find all the 6 functions, this is how you would do it. Find all the 6 functions. This is how you would do it. Okay? Now let's make it a little more difficult. The only problem is I don't want to squeeze it in to such a small space here. So I'm going to erase all of this and we'll go up on top with Roman numeral 3. We're still doing applications, but we're up to part B. So we're still doing Roman numeral 3 applications. But this is part B, and this is what the problem would say. Given the sine of theta is 3/7. And the question is, find the other 5. Trigonometric functions. This is a typical question that you will have to encounter most probably. You're given one function, what the value of one function. The question is, find all the other 5 trigonometric functions. How would you go about doing that? Well, what you would do is draw a triangle. This is theta. We know that sine is opposite over hypotenuse. So this would have to be 3. This would have to be 7. Sine opposite divided by the hypotenuse. Well, now knowing that, we're going to find all the other 5 functions. Well, if you're going to do that, then you're going to have to know what this third side is. So the first thing you do, step 1 in doing this problem, is to use the Pythagorean theorem. To find the missing side. So we need to know, if we want to, do all the other functions, we need to know what all the three sides are. We only know two. Therefore, we use the Pythagorean theorem, step one, to find the missing side. In other words, x squared plus 3 squared is equal to 7 squared. X squared plus 9 is equal to 49. X squared is equal to 40, and x is equal to the square root of 40. And what I really need to do in this problem is not simply say, find the other 5 trigonometric functions. I should say, find the exact value of the other trigonometric functions. And that saves us from having to use calculators to find out what this is to the nearest 10th or 100th or 1,000th or whatever. Okay, so just by saying find the exact values of the other, you could leave it as a square root of 40. Well, now we know that this is equal to the square root of 40. And therefore, the next step, step 2, will be to do the other 5 functions. Well, we know sine. Sine is 3 over 7. Let's just put that there. Sine is 3 over 7. Therefore, we also know the reciprocal function of sine, which is cosecant. That's the reciprocal. That's easy. Once you know one of the functions, you automatically know the reciprocal function, and that helps us to get rid of 2 of them right away. But now we have to do a little work. So cosine. The cosine of theta is equal to the adjacent over the hypotenuse. If you know cosine, you automatically know the reciprocal of cosine, which is secant, which is the reciprocal. So, that's why the reciprocal functions are so important, is because if you know the function, you automatically know what the reciprocal function is. That's great. That's really terrific. There's only one problem in this particular situation. You can't have a square root in the denominator. You can't have an irrational number in the denominator, and therefore, when you have the 7 divided by the square root of 40, you need to rationalize the denominator. Remember that stuff. If you get a square root in the denominator, you have to rationalize the denominator, and this becomes 7 times the square root of 40 divided by 40. Not just 7 times the square root of 40 over 40. It's really 7 times the square root of 4 times the square root of 10 divided by 40. So first you rationalize the denominator, very nice. Then you simplify the radical, which we've done before, a perfect square times another number. So this becomes 7 times the square root of 4, as you know, is 2, times the square root of 10 over 40. Now, you may be inclined to multiply 7 times 2, but even better than that is to cancel out the 2 with the 40, reducing a fraction. We've learned all this. This is all the tools that we've acquired in the past several weeks, which helps us to simplify expressions. And that's what we have. That's the answer to that particular question. We're not there yet, right? Because we've only done 4 of the 6 functions. Now, the other 2 functions, well, tangent of theta is equal to 3, the side opposite, over the square root of 40, 3 over the square root of 40. And you know what this means? Well, before we rationalize the denominator, let's do cotangent. Let's do cotangent. Because if the tangent is 3 over the square root of 40, then the cotangent is the reciprocal, which is the square root of 40 over 3. But you really have to do this. This has to be done. 3 times 2 times the square root of 10 over 40. Cancel out the 2 with the 40. And the answer is that the tangent of theta is 3 times the square root of 10 over 20. Okay, and the cotangent, which we got rid of to make room for the other thing, was the square root of 40 over 3. This is the answer to the question right here. All these things north of this line. I want to get everything in. Let's review what we did. Very important to always review what you did. The original question, given that the sine of an angle is equal to that fraction, find the exact value of the other 5 functions. So you use the Pythagorean theorem to find the missing side. Very nice, that worked out pretty well. Okay, very good. And incidentally, when you get the square root of 40, you could actually simplify this immediately, so you don't have to do it later. The square root of 40 is still equal to the square root of 4 times the square root of 10. So the answer would be that the missing side was not equal to the square root of 40, but was equal to 2 times the square root of 10. And then you get rid of it, very, very quickly. But anyway, we found it to be the square root of 40. And then knowing that information, we went back up to the top here. And I said the square, the sine of theta is 3 over 7. That's what was given. The reciprocal function would be 7 over 3, 3 over 7, 7 over 3. Cosine is the square root of 40 divided by 7. That's adjacent over hypotenuse. And the reciprocal function is 7 over the square root of 40, and that's when we had to rationalize the denominator. But I had all this room. That was real beneficial for the situation. And then we found the tangent, and we had to rationalize the denominator again. And then, using the tangent, we found the reciprocal function of cotangent. That's a typical problem. Given one of the functions, find all the other 5. And right now, I'd like to give you the opportunity of trying this. And I hope I'm not making a mistake, but I'm going to ask you to squeeze it in to this spot over here. Okay, so question, let's call this part C. Given that let's say the tangent of theta is 4 over 9, find the exact values of the other function. I'm going to begin. I haven't given you that much time to do this problem. I apologize for that, but I want to get it all in, so I'm kind of moving along at a good pace here. But this is how you would do it. So the first step is going to be, you want to draw the triangle. You want to draw the triangle. This is theta. Tangent is opposite over adjacent. And we need to know the hypotenuse, obviously, because if you want to find sine and cosine and their reciprocal functions, you're going to need the hypotenuse. So we need to use the Pythagorean theorem. 4 squared plus 9 squared is equal to x squared. 16 plus 81 is equal to x squared. Turning it around, x squared is equal to 97, and x is equal to the square root of 97. It's a simple problem, okay, but I'm still sitting back and I'm checking my work. That's what I'm doing right now. Okay, looks pretty good. Well, let's begin. The second part of the problem is going to be to answer the question. So, if the tangent of theta is equal to 4 over 9, then the cotangent of theta is equal to 9 over 4. Because cotangent and tangent are reciprocal functions. So if you know one of them, you automatically know the other one by simply flipping it over. So that takes care of tangent and cotangent. Let's go to sine. Okay, so sine. The sine of theta is equal to opposite over hypotenuse. But now the hypotenuse has a number attached to it. I don't think you could simplify the square root of 97. I don't think this, I don't think the square root of, I don't think 97 has more factors than just 1 and 97. I think 97 is a prime number. So we don't have to worry about breaking it down. So sine is equal to 4 over the square root of 97. Good. If we know sine, we also know cosecant. And that's going to be the reciprocal, the square root of 9. Oh, what didn't I do? What didn't I do that I need to do? I rationalize the denominator. So we need to multiply, we could write this over again, but you need to multiply by the square root of 97 divided by the square root of 97. That's 4 times the square root of 97 over 97. That's not a very pleasing number, is it? 4 times the square root of 97 over 97, but that's the answer nonetheless. And cosecant is much nicer to look at, right? Because that's equal to the square root of 97 over 4. So there we are. We've gotten 1, 2, 3, 4. And let's do cosine. Cosine of theta will be equal to the side adjacent, which is 9, divided by the square root of 97. Very nice. And we need to do the same thing, but we already know that this is going to be equal to, well, let's just do it. Let's just do it. Square root of 97, square root of 97, 9 times the square root of 97. Now, if you know cosine, you also know secant of theta is the square root of 97 divided by 9. There they are. And that's the answer to the question. Of course, if this were a test question, you'd have to circle stuff. Otherwise, I'd go crazy trying to find everything. This is one answer. This is sine and cosecant. So there's that, there's that, there's that, there's that, and that's really all there is. Okay? So given one function, we're able to find all 6 functions. Is there a question? Very important problem. I cannot emphasize properly how important this question is.
Professor, I have a question.
Yes, go
So
right
can you
ahead.
Yeah, so 4 is tan, and then 9 is the hypotenuse.
4 is the side opposite the angle.
Okay.
9 is the side adjacent to the angle. And the square root of 97 is the hypotenuse.
Oh, the 97 is the hypotenuse.
This is the opposite. This is the adjacent. This is the hypotenuse.
Okay.
Okay, a little confused there. That's okay. But the question is a very good question. We admire you, Valeria, for asking. You know, she was confused, so she asked the question, and now hopefully, you know, that's good. Okay. Anybody else? Okay, then let us move on to the next part of this whole thing. And Roman numeral 4. Now, so let's talk about angles. Let's talk about angles. These are the 4 quadrants. These are called quadrants. We mentioned this before. Quadrant 1, they're always indicated in Roman numerals. Probably because, you know, there's going to be so many numbers thrown around that Roman numerals kind of stand out. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. An angle is formed with an initial line and a terminal line. And this is what it looks like. I'm going to attempt to use my creativity to show you what an angle does. Initial line, terminal line. The initial line always stays put. The terminal line creates the angle. See that? The terminal line is what moves. The terminal line goes up and up and up. And when it gets to 90 degrees, this is 90, keeps going. Whoop, yep, there it is. And it becomes 180, 180 degrees. Where can I get a good picture here of it? 180. And it could keep going so that it goes to 270 degrees all the way around. And all the way back to the beginning is 360. So that's the way an angle is formed. And we're not going to talk about that so much as we're going to talk about angles between 0 and 90. And then after the break, we'll talk about angles, all kinds of angles, but let's just focus on the angles from 0 to 90. Now, there are special angles that we will be looking at. We'll be looking at special angles. And the special angles are formed because of what's called special triangles. This is the first special triangle. The 30, 60, 90 triangle. That's the first one. 30 degrees, 60 degrees, 90 degrees. This is 1. This is 2. If we wanted to find what this was equal to, we'd use the Pythagorean theorem. 1 squared plus x squared is 2 squared. 1 plus x squared equals 4. X squared equals 3. X equals the square root of 3. Therefore, the missing side is the square root of 3. This is what mathematicians came up with as a very, very nice way of finding the special angles, and you're using this particular special triangle. So there's three special angles. I should mention that. One of them is 30 degrees, one of them is 60 degrees, and the third one is 45 degrees. Those are the ones that come up in problems if you want to find the exact value. If you want to find exact values, we use those three angles because you could get the exact values. If you want to use an angle of 37 degrees, you can, but you're not going to get an exact value because it's going to come out to some weird decimal. But if you want to get exact values, you have to use those three angles, 30, 60, and 45 degrees. So this is how we derive the 30 and the 60. The sine of 30 degrees. Here's 30 degrees. The sine is the opposite over the hypotenuse. Therefore, the sine is equal to 1/2. The sine of 30 degrees is equal to 1/2. The opposite, the side opposite the angle, divided by the hypotenuse. The cosine of 30 degrees is equal to the side adjacent over the hypotenuse. And the tangent of 30 degrees is equal to the side opposite divided by the side adjacent. Do we have to rationalize the denominator? Yes, we do. The tangent of 30 degrees is the square root of 3 over 3. The cosine, the sine. We're not going to focus on the reciprocal functions right now. We're just going to focus on the big three. Okay? Now, let's look at 60 degrees. So, in other words, 60 degrees. The sine of 60 degrees will be equal to the sine of 60. Opposite over hypotenuse. Cosine of 60 degrees. Adjacent over hypotenuse. The tangent of 60 degrees. Opposite over adjacent. Square root of 3 over 1, or just the square root of 3. Notice the sine of 60 is equal to the cosine of 30. Sine of 60 is the square root of 3 over 2. The cosine of 30 is the square root of 3 over 2. Now you know where cosine got its name. Sine and cosine are co-functions. That means that the angles add up to 90 degrees, and they're equal. The co-functions are equal. Not reciprocal, fat reciprocal functions. These are co-functions, sine and cosine. Just keep that in mind. The sine of 30 is equal to the cosine of 60, because cosine is a co-function, because 60 and 30 add up to 90. They are co-functions, complementary, two complementary angles. You've heard, I'm sure you've heard this, maybe not. Complementary angles are two angles which equal 90 degrees. The co-functions 30 and 60. 30 and 60. Okay, just keep that in mind. I don't know. All right, these are 6 of the functions we need to know. In other words, if we were to establish a little chart, let's create a little chart over here. So I need to go down here. Sine, cosine. $30. What's the sine of 30 degrees? 1/2. What's the cosine of 30 degrees? The square root of 3/2. We just found that. This is all the work we did up here. I'm just summarizing it. Sine of 30 is 1/2. Cosine of 30 is the square root of 3/2. 60 degrees. The sine of 60 is the square root of 3/2. The cosine of 60 is 1/2. This is what we just did. Oh, and tangent. Oh, excuse me. Forgot about tangent. My favorite. Tangent of 30 was the square root of 3/3, and the tangent of 60 is the square root of 3. So there's only 2 ways of really knowing what the special angles are equal to in terms of the functions. Either you could derive it the way I just did, or you could memorize the chart. Your choice. Either you could derive it using the 30, 60, 90 triangle, or you could memorize the chart. Now, why did I have a 4th line over here, a 3rd line? This is for 30, this is for 60. Why is there a 3rd line here? Because I originally told you that there were 3 special angles, and the 3rd one is the 45-40, is based on the 45-45-90 right triangle. Now we're doing 45-45-90. So the sine of 45 degrees is equal to 1 divided by the square root of 2. The square root of 2/2. The sine of 45 is the square root of 2/2. The cosine of 45 is the adjacent over the hypotenuse, and rationalizing the denominator, we get that the cosine of 45 is the square root of 2/2 also. The sine and the cosine of 45 degrees are the same. They're equal to each other. And my favorite of all time is the tangent of 45 degrees. Can somebody in the class tell us what the tangent of 45 degrees is equal to? Let's see if anybody comes forth.
Is it 1?
Good. Tell us how you got that, Sandas.
Wait, because the tangent is opposite over adjacent, and opposite and adjacent is 1.
Good. Very, very nice. And we put it right in the chart. Good.
Professor, I have a question now. So
I
for
don't-
tangent, we always have to like divide it by its denominator.
You always have to divide it by its denominator.
Yes.
You always have to divide it by its denominator.
So 1/1, right? Last time it was
Yeah.
like,
Tangent of 45 degrees is 1/1. Yes.
yeah, so we divided by 1.
Okay. Yes. Yes.
And then
Well,
last
I
time,
mean, there's a reason why we divide it by 1. because the definition of tangent is opposite over adjacent, 1 over 1.
Mm-hmm.
So that's equal to 1, yes.
But like last problem, it was like, let's say tan equals 1 over radical 3, and then we multiplied it by its denominator.
Oh, yeah, because it was irrational, yeah, yeah,
Oh, okay.
because it was a radical, we want to get rid of the radical. But you don't
So
have
if
to get rid of the radical
Okay,
for this one, because there is no radical.
right.
Good.
Okay, got
Yeah,
it.
well, that, I mean, you're asking very nice stuff to clarify, Valeria. Really, really good stuff for the purpose of clarification. Good work. Good, very good work. Very good work. Okay. Now, you, as I said, you have a choice. The choice is you could either derive the special, the functions of the special angles. You could, the way I did it up here, you could derive this stuff using the 30, 60, 90 triangle, or you could, you know, like here and here, or you could simply memorize this chart. It's your choice. I mean, I don't, you know, what would I do? I did both. But when I was a student, I love this chart. And there are certain things about this chart that are very, very interesting to memorize. For example, sine, cosine, tangent. The sine of 30 is equal to the cosine of 60. The sine of 30 equals the cosine of 60, which equals, well, it depends, you know, well, okay, I mean, for one half. Sine of 30, cosine of 60. They both equal 1/2. That's, you know, because 30 plus 60 is equal to 90. Remember what I said? They're co-functions. The sine of 60 is equal to the cosine of 30. All right, so the sine of 30 is equal to the cosine of 60. Sine of 30, cosine of 60. They both equal 1/2. The sine of 60 is equal to the cosine of 30. The sine of 60 is equal to the cosine of 30. Because 60 plus 30 is equal to 90. So these are some ways you could figure it out. The sine of 45 equals the cosine of 45 equals the square root of 2 over 2. The tangent of 45 is the easiest because that equals 1. These are some hints as to how to make memorizing the chart easy. So in other words, if I'm filling in this chart, let me start from scratch. Sine, cosine, tangent. 30, 60, 45. This is it. This is the chart. The sine of 30 is 1/2. The cosine of 60 is 1/2. Right? The cosine of 30 is the square root of 3 over 2. The sine of 60 is the square root of 3 over 2. That's helpful. So you're able to do these two because of the relationship, this diagonal relationship over here. And the sine and the cosine of 45 is a square root of 2 over 2. So this is how I remember the chart. The tangent of 30, you just have to remember, is the square root of 3 over 3. The tangent of 60 is the square root of 3, and the tangent of 45 is 1. That's how I remember the chart. So if you look at this chart, it's not just a random chart you're remembering. there are, you know, things here that you could use to help you remember it. Or you could simply derive it the way I did down here for 45 degrees and for 30 and 60 up here. Okay? These are the special angles. And we'll be using these throughout the semester. This is something that is very, very important, that you know what the functions of the special angles are equal to. Because whenever we're talking about, as I said, the reason for this is the exact value you need to use 30, 60, and 45. Anything in between is not going to give you an exact value. These will give you, these are all exact values. Anything in between, like 18 degrees, like 21 degrees, like 62 degrees, like 47 degrees, will not give you exact values where you could, you know, just look at it and there it is. Okay? So one way or another, now, in my opinion, memorize the chart. You're going to need to memorize that chart. Okay?